Hello everyone, I'm Danel Ahman from the University of Ljubljana, and today I'm going to tell you about my joint work with Matija Pretnar on asynchronous computation in the context of algebraic effects. Without further ado, let me explain the motivations behind our work. Namely, in programming, we often strive for asynchrony, so as to have better responsiveness and better resource usage. However, despite all its successes, the conventional treatment of algebraic effects is unfortunately inherently synchronous. And by this I mean that when we are executing our program and we reach an operation call, then some implementation of this operation will get executed, but at the same time, the rest of the original computation is blocked, and it gets unblocked only when the operation implementation returns a value. Now, while this kind of blocking is indeed needed in certain situations, such as in the presence of general effect handlers, then unfortunately it forces all users of algebraic effects to be synchronous, even if this is not necessary nor desired. And while existing implementations of algebraic effects have also looked at asynchrony, then they have ended up simply delegating all the asynchrony to their language backends. Instead, in this paper, we set out to capture asynchrony for algebraic effects in a self-contained core language. In order to explain the core idea how we achieve asynchrony, let us recall how the operation calls are executed. If you look at this diagram closely enough, we can see that it actually consists of three distinct phases, involving signaling that some implementation of an operation needs to be executed, executing this implementation, and finally interrupting the blocking computation with the result of this operation implementation. Now, the core idea behind this paper is to decouple all of these three phases into separate programming constructs, so that the computation would not block and keep executing while the operation implementations are executing asynchronously, and also so that programmers could actually choose if and when they want to block the execution of their program so as to wait for the result of some operation implementation. And finally, so that programs could be interrupted spontaneously, so that we could model situations such as a user pushing a button or the environment preempting a thread. I'll now explain how we achieve these goals by extending general effectful lambda calculi with a number of programming constructs, and I'll explain them all one by one on the following slides. The first of our extensions to general effectful lambda calculi involves computations being able to issue outgoing signals. Here, op is the name of the signal, v is a data payload, such as a message we want to send to some server, and m is the continuation of the signal. Now, computationally, these signals behave a bit like algebraic operations in the sense that they propagate outwards in a computation, and the idea is that these signals want to reach the outer boundary of the computation so that they could be propagated further to other parallel processes. However, unlike algebraic operations, these signals do not block their continuation, so intuitively, when an execution of a program reaches a signal, then the signal gets issued, meaning that it keeps propagating outwards, and the continuation at the same time can keep executing on its own. To better explain how these signals work, let us consider a simple running example. In this example, there is a user process that scrolls through some data items provided by a client process. The client process provides a seemingly infinite feed to the user, whilst internally just keeping a finite cache of the items. And when the cache will start to run empty, the client asks for extra data from a server process. Now, in this situation, there are a couple of signals that we could be interested in. First of all, there is a signal that the client process could send to the server so as to request extra data when its cache is starting to run empty. And also there is a signal that the client process could send to some display process so as to display a message to the user. In addition to issuing signals, we propose that computation should also be able to receive interrupts, where op is the name of the interrupt, w is a data payload, and m is the continuation of the interrupt. Computationally, these interrupts propagate inwards into computations, so that's why we're using the down arrow notation. For example, interrupts propagate past outwards propagating signals, and they get discarded when they reach return values. So in this sense, despite looking very much like an algebraic operation call, interrupts actually behave much more like effect handling. And similarly to signals, interrupts also do not block their continuation, and most importantly, any sequence of reduction steps can be interrupted. So for example, if we're in the middle of executing a program, then an interrupt can appear at any moment, after which the interrupt term wraps itself around the current state of the program, and the entire program keeps executing, and the interrupt starts propagating inwards into M. And returning to our running example, let's look at a couple of interrupts of interest there. First, the client process could get an interrupt with the new batch of data issued by the server, and also the client process could get an interrupt with a request to show the next item to the user. Why we include interrupts as part of computations so as to explain their computational behavior, then we do not expect programmers to write these interrupts explicitly in their programs. Instead, these interrupts are commonly induced by signals issued by other parallel processes. To better explain this, let's return to our running example and consider the client computation and the server computation being run as two parallel processes. So here, on the left-hand side of the parallel composition operator, the client computation has just issued a signal to request a new batch of data from the server. What happens next is that this signal is propagated out from the computation and into the process land. Next, this signal is propagated past the parallel composition operator, which results in two things. So first, the signal keeps propagating outwards so as to find anybody else that might be listening to it. And on the right-hand side of the parallel composition operator, this signal has turned into an interrupt for the other process. And finally, this interrupt will be propagated into the other computation. However, not all interrupts have to originate from signals. They can also appear spontaneously, so that we could model situations like the user clicking a button or the environment preempting a process. So far, we have shown that computations can issue outgoing signals and receive incoming interrupts, but we haven't said anything about how computations could actually react to these interrupts. For this reason, we propose that computations should be able to install interrupt handlers, where we read this construct as making a promise to handle the interrupt op using the computation M in the continuation N. Now, while we are using the handlers terminology here, then computationally, interrupt handlers behave much more like algebraic operations in the sense that they propagate outwards in computations. Next, when an interrupt is propagated to a computation and it reaches a matching interrupt handler, then this handler code M is triggered, it gets executed, and its return value gets bound to the variable P in the continuation. And in addition, the interrupt gets propagated into the continuation. So this is further evidence that interrupts, while looking like algebraic operation calls, actually behave like effect handling. And when this interrupt doesn't match the interrupt handler that it reaches, then the interrupt is simply propagated past the interrupt handler. And finally, these interrupt handlers do not block their continuation, so this allows for asynchronous computation, but at the cost of having to reduce open terms. But what saves us when proving type safety for this calculus is that this variable that we bind in the continuation does not get assigned an arbitrary type, but rather a distinguished promise type that denotes values that might not have been computed yet. While all the constructs we have discussed so far have been non-blocking in their computational behavior, then we also provide the programmers with a means to selectively block the execution of their programs by explicitly awaiting on a promise to be fulfilled. This awaiting construct reduces when it's provided with a fulfilled promise value, but it blocks the execution of its continuation when it's provided with a yet to be fulfilled promise, such as one of the variables that we bind in our interrupt handlers. Returning to our running example, the client process could use this awaiting construct to block its execution until the server has sent it its configuration, such as the batch size that it uses. Finally, with this await construct, we have all the pieces together to be able to express algebraic operation calls as discussed before. In particular, this involves signaling that some implementation of the operation needs to be executed and installing an interrupt handler so as to react to when this implementation interrupts our program. In addition, we use the await construct to block execution until this interrupt arrives. And the implementations of this operation are then defined in parallel processes as follows. Let us now return to our running example to demonstrate how programs written in our approach usually look like. First, the client program immediately demonstrates the benefits of asynchrony, because in between issuing a signal to request the server settings and blocking its execution, the client code can actually do some useful work. In particular, in this case, this involves allocating some auxiliary memory references. Meanwhile, the main loop of the client is given by a recursively defined interrupt handler that reacts to the next item interrupts coming from the user and turns them into display signals and new data requests. The recursive definition is needed so as to reinstall the interrupt handler after handling each of the next item interrupts. At the same time, the server process is given simply by two recursively defined interrupt handlers that react to and handle the interrupts originating from the client process. And this kind of recursively defined interrupt handler-based definition is quite common to server-like processes in our setting. We can also model the user as a process that simply sends out the next item requests every once in a while. And finally, somewhere there would also be a display process that would react to the display signals issued by the client. One of the main contributions of our paper is to turn the ideas that we have discussed so far into a type-safe core calculus for programming with asynchronous effects. In the following slides, I'll briefly introduce the calculus and describe its properties. This calculus is an extension of the fine-grained callback value lambda calculus with fulfilled promise values, general recursion, and all the previously shown computation terms. In addition to values and computations that we inherit from the underlying calculus, we also include a separate class of processes. These contain individual computations being run in parallel and parallel compositions of processes. Processes also include signals and interrupts so as to communicate them between different processes. We also equip our calculus with a type system defined using three typing judgments, one for values, one for computations, and one for processes. The value types are given by extending the value types of the underlying calculus with the type of promises. And amongst these value types, we carve out the subset that we call ground or mobile types that we use to assign types to the payloads of signals and interrupts. And importantly, these types do not include the promise type, because the mobile types are meant to classify values that can move between different processes, whilst the promise type values should be kept local to each of the individual computations. For computation types, we follow the standard approach of pairing the type of values that the computation returns with some effect annotations. In our case, the effect annotations describe both the signals that the computation might issue and also the interrupt handlers that the computation might have installed. Now, while the signal annotations are defined as standard, simply given by a subset of the possible signal names, then the interrupt handler annotations are actually given by an interestingly recursive structure. In particular, each of the interrupt handler annotations is a partial mapping from interrupt names to the effects that the corresponding interrupt handler code might produce when triggered. And finally, for process types, we simply mimic the structure of the processes at the level of types. Next, let's look at some of the more representative typing rules of our calculus. First, for typing outgoing signals, we require that the signal is included in the corresponding effect annotation and that the type of the payload value matches the signal's signature. Next, when typing incoming interrupts, we again require that the type of the payload value matches the interrupt signature, but more interestingly, the interrupt also acts on the effect information. And this corresponds to the idea that when this interrupt is propagated to the computation M, then it will trigger the corresponding interrupt handlers, and correspondingly, we need to reveal the effects of these interrupt handlers at the level of effect annotations. And finally, when typing interrupt handlers, we first look up the effects that ops interrupt handlers are allowed to have, and then type the interrupt handler code M against the specific effect information. Furthermore, the variable p that we bind in the continuation of such an interrupt handler is not assigned an arbitrary type, but rather our distinguished promise type. And as mentioned before, this is crucial for establishing type safety for our calculus. We also equip our calculus with a small step operational semantics defined using two reduction relations. These reduction relations are defined in terms of the standard reduction rules that we inherit from the underlying fine-grained callback value lambda calculus, and the rules that we have seen so far in the previous parts of this talk. But in addition to these rules, we also have a rule that allows signals to commute with interrupt handlers. And this is so that signals could reach the outer boundary of a computation and they could be propagated to other parallel processes. What's interesting here is that this rule single-handedly makes the type safety proofs actually interesting. Because if you look at the left-hand side of this rule, then the data payload of the signal is under the binder of the interrupt handler, whilst when you look at the right-hand side of this rule, then this payload value has moved past this binder. For type safety proofs, this means that we have to be able to strengthen the typing context of this payload value by throwing this variable away, but luckily, as we haven't allowed promise type values to be used in payloads or payloads to depend on them, then we can do it. And finally, we also include the evaluation context rules. As already mentioned on multiple occasions, we also prove our calculus type safe. As usual, we split the type safety proofs into a progress theorem and type preservation theorem. For progress, we prove the usual statement that given a closed, well-typed computation, then it either can take a step of reduction or it is already in a result form. In our calculus, this means that when considered as a computation tree, then M has a shape where signals are towards the root, the intermediate nodes contain interrupt handlers, and the leaves contain blocked awaits and return values. And in order to ensure that M can take a step of reduction if it's not in a result form, we rely on evaluation context only binding promise type variables and not arbitrarily typed variables. For processes, the statement of progress is also unsurprising, and here a process is in a result form. If considered as a computation tree, it has signals towards the root, parallel compositions in the intermediate nodes, and individual computation results at the leaves. Regarding type preservation, then for computations, we prove the usual statement that when a well-typed computation takes a step of reduction, then the resulting computation is also well-typed at exactly the same type. And it's actually the proof of this theorem where we use the fact that the payloads of our signals and interrupts do not include or depend on promise-typed values. And as explained a couple of slides ago, this is needed in order to strengthen the typing context of payload values by throwing away the variables that are bound in interrupt handlers. For processes, we prove a variation of the usual type preservation statement, where we do not insist that the resulting process is typed exactly at the same type as the original one, but rather allow it to be typed at some other type that is related to the original one by a type reduction relation. And intuitively, this means that the type Q is the result of acting on the type P with some number of interrupts. And in turn, this models the situation where an outwards propagating signal in one parallel process creates new inwards propagating interrupts in processes parallel to it. Having developed this core calculus, we also applied it to a number of examples so as to demonstrate its general usefulness. Probably the most noteworthy of our examples is that of preemptive multithreading, but I'll return to this example in more detail on the next slide. In addition, we also showed how to implement remote function calls, which is generally one of the main applications of asynchronous computation. We also showed how to implement the concurrent version of runners of algebraic effects, where we separate the user code and the runner into two parallel processes. We also demonstrate how to post-process promised values in a non-blocking way. And by this I mean that, for example, if an existing interrupt handler has promised to return us a list of integers, then we show how to apply further functions to this list without blocking the rest of the computation and in such a way that these functions get executed only when the original interrupt handler is triggered. And finally, we can also implement go-like select statements in our calculus, which we can then use to simultaneously wait for a number of interrupts and only react to the first one that arrives. And now, as promised, I'll show you in more detail how we implement preemptive behavior in our calculus. When we can already express a wide range of evaluation strategies using the conventional treatment of algebraic effects, then unfortunately these evaluation strategies end up being very much cooperative in nature, in which each of the threads needs to explicitly yield back control, stalling other threads until it does so. And while it's possible to also simulate preemptive multithreading in the conventional treatment of algebraic effects, then as with simulating asynchrony, it again requires low-level access to the specific runtime environment of one's language. And in this case, this access is needed to insert these explicit yields into one's running computation. However, in our calculus, we can actually express preemptive behavior directly, and we don't have to rely on any specific underlying runtime environments. And the way that we do it is simply by prefixing the computation that we want to run in a preemptive mode with a special function, where the special function is defined in terms of interrupt handlers for stop and go interrupts. Now, when we call this function, then first the interrupt handler for stop gets installed, but in such a way that we do not block any consequent computations, including the computation comp that we're interested in. However, if a stop interrupt arrives and this interrupt handler is triggered, then we install another interrupt handler for the go interrupt, but in this case we are blocking the rest of the computation using the wait construct. And finally, when the go interrupt arrives, then this last interrupt handler gets triggered, the await gets unblocked, and we recursively call our special function again so as to reinstall the interrupt handler for stop and repeat the cycle. Our paper also comes with a software artifact, which consists of two things. First, there is an Agda formalization of our core calculus and its type safety. It's worth noting that in the Agda formalization, we implement a slight variant of the calculus that we present in the paper, because we only work with well-typed syntax so as to make working with de Broglie indices a bit easier, and as a result, the subsumption rule becomes an explicit coercion in the Agda formalization. And in addition to this formalization, the paper also comes with a prototype implementation that includes an interpreter that implements the operational semantics that I've shown you in this talk, and a simple type checker that unfortunately doesn't yet check for effect information. We have used this prototype implementation to implement all the examples that you have seen in this talk and that you can find in the paper. And this prototype implementation comes with two interfaces. First, there is the command line interface that simply executes only one of the many possible non-deterministic reduction sequences of a given program. But then there is also the web interface that allows programmers to explore all the possible reduction sequences of their programs. As an example, this is how the web interface looks like. On the left, you have the program that we are in the middle of executing, and on the right, you have the possible steps that you can make during executing this program. So, for example, you can make some number of random steps, you can trigger specific active redexes, and you can also manually send interrupts to your program so as to model an environment that, for example, wants to preempt a thread. Before concluding the talk, let's also look at some of the future work directions. First, as I told you, the current prototype implementation doesn't do any sort of effect checking, but this would be nice to have. In addition, having our very precise type and effect system at hand, it would be also nice to be able to use it for effect-dependent optimizations. For example, given a computation whose type says that there are no interrupt handlers installed for a given interrupt hop, we would simply want to be able to discard this interrupt if it arrives at this computation. Also, we would like to refine our currently very liberal communication strategy, where we are broadcasting everything to everywhere and everybody. We're also working on accommodating more general payloads and the dynamic creation of processes in our calculus. And in this case, Fitch-style model types have been very useful so as to generalize the idea of what we can consider as a mobile type and the mobile value. And we're also looking into the denotational semantics of our calculus based on monads for scoped effects. And the idea here is that if you squint enough, it becomes obvious that our interrupt handlers are just an instance of general scoped algebraic effects. And finally, it would be interesting to do a more in-depth comparison with the message passing concurrency frameworks, because as many of you have probably already spotted, our calculus has many joint features with calculi such as the bicalculus, the joint calculus, and the actor framework. In conclusion, we have shown how to incorporate asynchrony within algebraic effects by decoupling algebraic operation calls into signals and interrupts, and by allowing programmers to install interrupt handlers and selectively block the execution of their code. We have also shown how to distill these ideas into a core calculus for programming with asynchronous effects, and we have applied this calculus on a number of examples, ranging from preemptive multithreading to remote function calls and others. And finally, the paper is also accompanied by an Agda formalization of the core calculus and a prototype implementation of it. That's it for now. Thank you all for listening, and see you at the Q&A session.